Welcome back to the deep dive. Today we are strapping on our atomic goggles, so to speak.
Ah, yes.
We're taking a really close look into high-strength steel, and not just any steel. We're focusing on AISI 4340.
That's right.
You know, the kind of material that's absolutely critical for things like landing gear, really high-stress parts in vehicles, advanced tools. It's known for its toughness after quenching and tempering.
It is, but we're going deeper.
Much deeper. We're looking at the phase transformations, the physics happening at the micro level that gives it that strength.
Exactly. Our mission today is to dig into sources that try to understand and really rationalize why there are these distinct structural differences, these two types of martensite that form when you cool this steel rapidly.
Lath martensite and plate martensite.
Lath and plate, yes. One looks like bundles of, well, laths structured. The other is sharper, more like individual plates.
And the core question is about the fundamental unit of transformation, isn't it?
Precisely. Is it the individual lath or this bigger structure, the lath packet? Understanding that is key to predicting the final mechanical properties. We really want to grasp the structural mechanics right down at the atomic level.
And that's why this matters to you, our listeners. Whether you're deep into material science or just, curious about how things work.
Absolutely.
AISI 4340 is a workhorse in high-stress engineering. Understanding if it transforms piece by piece, or more like a coordinated team, that fundamentally changes how we think about its strength and, crucially, its resistance to failure.
It really does. That difference between individual versus cooperative transformation is kind of a game changer.
Okay, let's unpack this then. Where do we start?
Let's start with the material itself. AISI 4340. It's a well-known high-strength, medium carbon, low alloy steel.
Low alloy, meaning it had specific additions but not huge amounts.
Correct. The composition is finely tuned. We're talking weight percent here. Carbon is key at 0.38%.
Medium carbon, right?
Yep. Then manganese, 0.59%, silicon, 0.37%, chromium, 0.84%, and molybdenum, 0.60%.
But there are a couple of others that are really significant for the transformation process itself, aren't there?
Oh, absolutely. Nickel, Ni, is a big one at 2.89%. And that molybdenum, Mo, at a 0.60% also plays a role beyond just strength.
Okay, so what do the nickel and molybdenum do specifically in this context?
Well, nickel is crucial because it significantly lowers the temperature where martensite starts to form the Edmonds temperature.
Okay, so it shifts the whole transformation window downward.
Exactly. It happens over a different lower temperature range. And molybdenum, that primarily boosts hardenability, making sure the transformation happens effectively even with slower cooling rates than, say, pure water quenching.
So this specific chemical cocktail is designed to give us a quenched structure that's naturally a mix of both lath and plate martensite.
That's the result, yes. A
Yeah.
mixed microstructure.
Which brings us right back to that core dilemma the sources tackle. When that parent crystal structure, austenite, flips to martensite, what's actually happening? Is the smallest unit, the individual lath, the main actor?
Or is it the larger group, this lath packet?
And why is knowing which it is so critical?
It boils down to strain energy. The martensitic transformation involves a huge rearrangement of atoms, a significant shape change at the atomic level.
Right, it's like trying to fit a slightly different shaped block into a hole. Create stress.
A lot of stress. Internal stress, what we call elastic strain energy. Now, if the transformation happens lath by individual lath, each one creates its own intense, localized stress field.
Okay.
But if it proceeds via a cooperative lath packet, the laths move more or less together. They share the load, accommodate their neighbors' strain fields.
Leading to lower overall internal stress for the whole group.
Much lower. It's a more stable, lower energy configuration.
So the packet structure is essentially the steel's way of managing that transformation stress more efficiently, finding a kind of structural harmony through cooperation.
That's a good way to put it, yes. And this cooperative nature is linked to its toughness.
And the sources used some pretty powerful microscopy to figure this out.
They did. Transmission electron microscopy, TEM, looking at really thin slices of the quenched steel. This allowed them to actually see the structures and map out the relationships between the laths and plates.
What did they find visually?
Well, first, they confirmed the microstructure is a mix of lath and plate martensite, often partially developed. But the really crucial finding, based on how these structures were arranged, was that the lath packet really is the fundamental transformation unit, not the individual lath.
Okay, hold on. If the packet is the unit, what defines its boundaries? Especially compared to the boundary of a single plate. Are they different?
That's a very important point. Yes, they are fundamentally different. For lath martensite, The boundaries between the parallel laths within a packet,
Yeah.
those are the habit plane.
The habit plane. Remind us what that means again. It's not just any boundary.
No, definitely not. It's a very specific crystallographic interface. It's the plane where the parent austenite and the new martensite lattice meet with the least possible mismatch, the lowest strain energy.
The path of least resistance, atomically speaking.
Precisely. So the laths within a packet align along these low-energy habit planes, which strongly suggests they formed cooperatively.
Okay, that makes sense for the laths in a packet. But what about the plates? What are their boundaries like?
The plates are different. Their boundaries are described as a polygonized dislocation arrangement.
Polygonized dislocation. Sounds complex.
It is. Think of dislocations as tiny imperfections or line defects in the crystal structure. Polygonized means these defects have arranged themselves into a more ordered, structured boundary, almost like a tiny grain boundary itself.
So not a simple low-energy habit plane like the laths use.
No, it implies the plate formation involves a much more complex mechanism for managing that transformation strain. It's a higher energy boundary structure.
That structural difference is pretty telling, but wasn't there some physical evidence, something they saw that really nailed the case for the packet being the unit?
Yes, absolutely. It came from looking closely at the stuff between the laths, specifically retained austenite.
Austenite that didn't transform. Leftover parent phase.
Exactly. The rapid cooling traps small amounts of the original austenite structure. And the sources observed very thin films of this retained austenite sandwiched between the parallel laths that make up a packet.
Okay, I see the film exists, but how does that prove cooperation? Couldn't laths just form one after another and trap some austenite between them?
You could think that, but the key is the stability of that film and what it implies about stress. If laths formed independently, the intense localized strain fields around each one would likely either force that austenite to transform or even cause microcracks. The fact that this thin, relatively weak austenite film remains stable between the laths suggests the stress is being managed cooperatively. The adjacent laths in the packet have complementary strain fields that partially cancel each other out across that boundary.
So the film acts like a buffer, surviving, because the overall stress from the cooperative packet is lower.
Exactly. It's strong evidence that the whole packet transformed as a unit, sharing and reducing the strain, allowing that austenite cushion to persist. It's a signature of that cooperative mechanism, which, again, links back to the material's toughness.
Right. Fascinating. So we've established the lath packet as the main player, the fundamental unit.
Yes.
But plates do still form. If the packet is so good at managing strain, why does the steel sometimes form plate martensite?
Good question. This brings us to the factors that control which morphology forms. And a major one is the initial austenite grain size.
The size of the crystals before you quench the steel. That makes intuitive sense. Bigger spaces might allow for different structures.
Precisely. The sources found a pretty clear relationship. When the initial austenite grains were relatively small, say around 100 micrometers or less.
Which is still pretty small to us, but maybe not atomically.
Right. In those smaller grains, they mainly saw what was termed half-lath morphology, sort of underdeveloped lath structures. But once the grain size got bigger, above that 100 micrometer threshold, that's when they started observing fully formed plates, sometimes quite large, both inside the grains and crossing grain boundaries.
So larger grains provide the necessary real estate for these big, likely high-strain plates to form.
It seems so. Space is a critical factor.
And when a plate does form, you mentioned earlier, is trying to minimize elastic strain energy.
Yeah.
How does its structure help with that, especially at the tip?
Right. Nature always seeks the lowest energy state. Plate formation, particularly when it happens at the higher end of the martensite transformation temperature range, it needs to minimize that strain energy cost. The sources talk about the plate tip showing degenerate behavior.
Degenerate. That
Yeah.
sounds bad. Or technically specific.
Yes, technically specific. It doesn't mean failing. It means structurally simpler. The growing plate tip minimizes its high-energy interface, the sharp curvature at the very front. By simplifying its internal crystal structure right at that tip, it becomes less complex, crystallographically speaking. This structural simplification, or degeneracy, is associated with having just a single tip, which lowers the energy barrier for the plate to advance.
Wow. Okay, so it sacrifices some internal complexity right at the leading edge to make moving forward easier, energetically speaking.
That's the idea, a clever atomic-level strategy.
Now, there's one more layer here. Twinning. The sources found twinning within the plates.
Yes, twinning is another way crystals can deform or accommodate stress. It's like creating a mirror image of the lattice across a specific plane.
A stress relief mechanism.
Exactly. But the sources found that twinning was only partial, it didn't always cross the entire plate. And critically, it mostly involved just a single variant, a single type of twin plane.
Why is that limited nature important? What does it tell us?
It suggests the principle of least effort. Again, twinning was most common when adjacent martensite units were already in a twin relationship.
Ah, so if the neighbors were already aligned in a way that helped manage the strain mismatch.
Correct. If the local environment already provided some strain accommodation through that existing twin relationship, the growing plate didn't need to go to the energetic trouble of creating lots of new, complex internal twins.
Especially since these plates form at higher temperatures, where the driving force for transformation is a bit lower anyway.
Precisely. It all fits together.
Okay, let's try to synthesize this. We started with this super tough steel, AISI 4340.
Right.
We drilled down into the two main structures, lath and plate martensite, that form when you quench it. And the big takeaway seems to be distinguishing between the individual lath as just a building block.
And the lath packet as the actual functional cooperative unit that undergoes the transformation.
That's the fundamental unit.
That seems to be the consensus from the sources, yes. The whole process, the choice between morphologies, it's all driven by managing that transformation strain energy.
So the lath packet is the efficient cooperative solution.
Generally, yes. And the plate morphology is what happens when conditions like larger grain size or higher transformation temperatures favor minimizing that sharp interface curvature energy, even if it means a more complex boundary structure overall.
So the sources effectively rationalized why you see both morphologies. The packet is the default cooperative unit, and plates form under specific conditions governed by interface energy and available space.
That's a very good summary of their conclusions, yes. The lath packet is fundamental. Plate formation is about minimizing interface curvature in specific situations.
Okay. So thinking about where this leads.
Well, it raises a really interesting question for you to consider, doesn't it? We know elements like nickel are added specifically to lower that transformation start temperature, the
Or shifting the Miss-MEF range.
So given that the lath packet seems to be the preferred low-energy structure, especially perhaps at lower transformation temperatures, and plates might be favored higher up, how could you perhaps tweak the alloy composition? Maybe slightly more nickel, or altering the molybdenum?
To deliberately push the transformation towards favoring more lath packets, or perhaps even suppressing plates.
Exactly. Could you engineer the alloy chemistry to reliably favor one morphology over the other by controlling that critical temperature range?
And if you could, what would that actually mean for the final properties? Would maximizing lath packets give you the ultimate toughness, or is some mixture ideal?
That's the multi-million-dollar question for materials design, isn't it? How to precisely control that microstructure for optimal performance in really demanding applications. Something to think about.
Absolutely fascinating. A great point to ponder. Thanks for joining us on this deep dive into the intricate world of steel crystallography.